Hi, good morning, good afternoon to everyone who's dialed on today. My name's Shimi and I would like to welcome you to part two of the Cumberland Energy Generator Monitoring webinars. An interesting fact that we've been sharing during these webinars is, did you know the potential cost of having a generator shut down due to a failure can be in the region of $300,000 per day? This figure can be much higher depending on the size of the generator. Throughout the two webinars, we'll delve into key aspects of generator monitoring, highlighting the current and future risks, the failure mechanisms, and the important topic of data analysis. In today's session, you can expect to learn about stator winding failure mechanisms and the characteristics of partial discharge, analysis of the phase resolved partial discharge patterns and trending analysis, and the importance of correlating online partial discharge data with the operating conditions. Throughout the webinar, should you have any questions that you will wish to ask, please post them in the chat section and we will review these during the Q&A at the end of the presentation. Now, if I can hand you over to Nathan Jacob.
Great, thank you for the introduction. So the presentation here today, the focus is going to be on interpretation. So interpretation of the data collected from generator online partial discharge monitoring. We find that many asset managers are, understanding that partial discharge is a useful tool, but the complexities of the data, how it's visualized, how to trend, how to interpret, this is still a challenge for many asset managers. It's not a topic that is kind of well understood universally. Okay, so the focus in this webinar is to present some of the concepts from a high level and give some intuitions, about how to look at the data, how to analyze the data, comparing it to operating conditions, doing trending, and also looking at some of the distinctive indicators of certain defect types. Okay, so as we get into it, first, just to preface and give an introduction relating to what partial discharge is. Okay, so if this is not understood, but partial discharges are essentially defined in standards as localized electrical discharges. So these are smaller discharges, not arcing discharges or discharges that fault directly to ground, but really electrical discharges that are partially bridging between the high voltage to the grounded or low voltage conductors. Okay, and it can occur internally within the insulation system, but it can also occur adjacent to the conductors on surfaces. Okay, so considering kind of the more traditional electrical discharge starting as maybe a void. So if you have high voltage up at one of these terminals here at the top of this on the black bar, and then the other conductor is either an opposite polarity voltage or a lower voltage or ground. If we have a void within the material, because it has a lower permittivity than the surrounding material, okay, it's going to have higher electric field stresses at that location. And discharges can start in this void, and there's the energy created by the discharges create some byproducts. Some may be conductive, okay, and these may lead to the spread and the growth of that void, an increasing size of the defect. We can see electrical trees here in the illustration. And once you've, had some defect and some carbonization of the materials are now compromised, they're weakened. So when you have a system disturbance or even just potentially under normal operating conditions, this defect makes it so that you can no longer sustain the voltage between the high voltage and the grounded conductor, and we have a breakdown or failure. So partial discharges, they're an early warning if we can detect them in the very early stages. Then we have the option to take interventions and prevent something like an in-service failure from occurring. What it looks like in the real application, of course, so within rotating machines, hydro generators and turbo generators specifically, we have the stator winding insulation is where we have the presence of high voltage and grounded conductors, or the grounded core, I should say, where that electric field stress can create the potential for partial discharge. And the partial discharges can occur at different regions within the insulation system. So we see here an example. These strands here, this is a cross section of an actual copper winding, an actual machine winding. And you can see here large voids in the material. And voids in the material would be like the void on the previous illustration. So these would be high electric field stresses at those sites, and we would have discharges potentially at those sites that may weaken the insulation over time if they're persistent and high enough of energy. And you can have a failure of the machine as a result of that. Okay. Particularly concerning are if there's voids, at the site immediately adjacent to conductors, because the electric field stress would be even higher at those sites, right? But you can also have discharge at other locations. So here we can see between two bars in the end arm regions, you see this white chalky substance is the formation of nitric acid at this location. And that deposit is indicative of high electric discharge activity at this site, okay? Eventually, this site may have some carbonization on the material surfaces, and in a similar fashion as described for the void case, you may have a weakening of the overall insulating level of the winding, and a failure could occur at that site. Similar to here, here's a indication again by the white chalky substance seen visibly here, that there's discharges due to defects in the winding between the overlap of the end winding insulation into the slot section of the coil before it enters the core. Okay. Each of these defects have their own distinctive behaviors, okay? And that's going to be very key as we talk about interpretation. But the distinctive characteristics are that they each have their own relationships with operating conditions, namely. So this is going to be part of the importance of continuous online monitoring. If we can monitor load, temperature, relative humidity, sometimes those factors play a role in surface discharges like the ones that appear in the end winding regions. And then also load and temperature. Load and temperature play a key role as an operating condition for discharges occurring inside the insulation system. So inside of the bar and coil cross section of the insulation, like shown here in the picture. So we know online partial discharge is important because a lot of the industry surveys indicate that to us that for hydro units, many of the failures are attributed to insulation damage. And the insulation damages, the type of failures that occur, the gross majority of these can be detected by partial discharge monitoring. Okay, so most of these root causes, whether they're related to internal discharges, like we talked about in the cross section of the insulation of the bar or coil, or whether it's related to contamination on surfaces. But we know that each of these defects can ultimately lead to failures due to insulation damage, and each of them would be detected. There's early warnings that can be indicated by the majority of these by detecting online partial discharges. Okay, so we know that it's very important as a condition assessment tool to affect condition-based maintenance on the basis of detecting any of these potential defects if practicable, if we can actually affect a change, whether it's a rewind or some cleaning of end arm regions. We want to choose an effective maintenance to address any of these defect types if we can detect them early. The picture is quite similar for turbo generators. So this is, fossil fuel based, whether they're coal or natural gas turbo generators. And the stator winding here, the electrical insulation associated with the stator winding, it's the second most leading cause of failure of the overall generator. Okay, so the highest is the rotating components, but when we consider the stator winding insulation along with the core and frame, and considering that as one entity, right, these would constitute a larger portion of overall failures. So again, the insulation systems of turbo generators very similar to the hydro case. So they would have many of the same failure modes and characteristics of failure that we can detect through online partial discharge monitoring, like already mentioned. So if we consider, conventionally or traditionally how this has been approached, the traditional approach for online partial discharge measurement for generators has been historically kind of periodic tests. So these would be tests where technicians go out with a portable instrument and connect the portable instrument to sensors which are terminated externally to the generator housing. So you can see here the image of a sensor installed on a hydro machine. The sensor is connected into the high voltage winding of the generator. And this would allow us to detect the higher frequency partial discharge pulses that are occurring inside the generator winding. Okay. Now, there are drawbacks to this approach. One drawback that some asset managers are considering recently is just the operation and maintenance drawback. The need to send technicians into the powerhouse to go to each generator and to collect data can be undesirable just for O&M costs reasons. Okay, but the other key reason, if our focus is to detect problems and identify failure modes early, uh, some PD phenomena are intermittent, okay? And because of this intermittency, the discharges may not be active when we perform this PD measurement, okay? Another trait of the conventional approaches to online PD monitoring is the assessment of the discharge based on magnitude. Okay, so many utilities collect the partial discharge data and they look at how the magnitude of those discharges compare to a large population of data in a data set. Okay, so generally, utilities would consider, okay, if the magnitude of the discharge is greater than 90% or 80% of all the measurements performed for generators at that voltage class, then that would trigger some warning for them, okay? The problem with that approach, though, is that it can lead to errors in assessment. So if you look at this illustration on the right, and we imagine this is a schematic representation of a machine winding, okay? But imagine the winding as a large number of connected bars or coils in series with one another, forming a large inductance, essentially, okay? So this large inductance of the winding, when you have electrical discharges, they get attenuated as they propagate through the winding. So if we consider a discharge source very deep in the winding, even if it's large at the very site of where the defects are, by the time it propagates to the sensor located within the winding, there's going to be some attenuation. So we can see here the attenuation of the pulse compared to the attenuation of the second pulse here, which is at a closer site to the sensor, it's going to appear as larger. Okay, so what this can do is that you can have sort of an assessment that's in error because the discharges can occur within the winding at various locations. Now, arguably, the sensors being closest to the highest voltage location may be the most prone to high voltage PD, but you can have partial discharges as a result of vibration or deterioration of the slot that aren't necessarily so dependent on voltage magnitude, okay? And we can make an error in diagnosis because the pulses appear small at the sensor because we're only comparing them to severity. That would, have a problem that is a very serious defect, only showing as something that's not so serious because we're comparing to just magnitude. So other limitations are related to quantitative metrics kind of carrying low information, okay? So traditional approaches looking at these pulse height analyses tables or diagrams where you compare pulses and repetition rate to the magnitude and kind of using it as a visual comparison of the magnitude of the negative pulse polarities versus positive is a bit limited in the sense that we can't always use it to diagnose specific failure mode types, right? Um, Also, if there are multiple defects present and active in the winding, that also may obscure the ability to make these kind of assessments based on these metrics. So in that way, there's a bit limited diagnostic value. Also, some older acquisition systems that many utilities use for many years, they have low fidelity in kind of looking at the partial discharge pattern. So I talked about different defects have distinguishing features. One of the best ways to identify defects types is to look at the phase result partial discharge diagram. We can see the diagram here and the pulse pattern. These are indicating the phase location and relative magnitudes of the partial discharge pulses relative to the voltage stress, okay? And these patterns are quite useful at identifying certain defect types. But, older technologies being kind of lower fidelity, lower sampling rate, or technologies that don't denoise signals and separate discharges which are occurring on one phase from another in a way that's well and makes the patterns easily discernible, uh, can be less effective in allowing for you to assess this way. Okay, so considering that, some of the benefits of modern online partial discharge monitoring for generators is that one, many are permanent and continuous. Okay, so having a permanent and continuous online monitoring system versus one that requires periodic measurements. Of course, there's the O&M benefit in the sense that it's lower cost maintenance wise, but it also uh, provides benefits where if you're operating in a continuous way, you can also have the system ingest operating condition data, load and temperature, relative humidity. Even if there are independent sensors for other winding monitoring, such as winding vibration, these can be important tools for diagnosing problems through looking at correlations in the information. Correlations, like I mentioned, for the certain stator winding defects, they're well correlated to operating conditions, loading and temperature. And the other benefit is with modern systems and the removal of noise, we end up with like high fidelity discharge patterns where we can clearly see defects. And in the example here, you can see the presence of two defects. The one here in the kind of triangular pattern with larger magnitude discharges on the negative half cycle and positive polarity is indicative of a slot discharge pattern. But there's also a pattern present here for positive polarity. Okay. And if we're limited in the ability to visualize this pattern and we're limited in the ability to compare, just with the traditional metrics like the magnitude or the ratio of positive to negative magnitude pulses, we're going to have less ability to discern the presence of this defect, right? So it's through correlations, identifying anomalies in the data, through trending and correlating the information, and also the high fidelity that we get with modern acquisition systems to visualize the PD patterns that enable better detection of defects and also improve our ability to assess the condition. So condition assessment depends on the quality of the data. So we're very focused, some of these points have already been mentioned, but denoising to remove external discharges or crosstalk in measurement, and also to have good quantitative metrics for trending data. The phase result PD diagram is very important for identifying certain defect types and trending the data. We want to look at trends over time. Okay, so with continuous systems, we have the ability to see if there are defects that are in very early stages and only intermittent. And the trending through continuous data also gives us the ability to extract information about how the discharges behave related to the operating conditions. So we can ingest data from the load, the temperature information, ambient air, and relative humidity. Okay, so in this way, for effective online partial discharge monitoring and the most effective interpretation of the data that you're collecting, continuous monitoring is ideal in this instance. So just to kind of go through some defects and speak to their characteristics, because we are hoping to kind of convey some information here about interpretation, I'm just going to show a subset of certain failure mechanisms and speak to how they can be identified by looking at the data. So for the most standard discharge types, ones that are related to voids in the machine insulation or the winding insulation, we look at standard mechanisms relating to that discharge, where we see in the phase resolve diagram, very symmetrical behavior where we see similar pulse polarity and pattern in both half cycles. So when you look at the phase result diagram, you'd be looking to see that the pulse magnitudes are roughly equivalent. Okay. The characteristics here are also inversely proportional to temperature. So you might see at lower temperatures when the machine is just starting, or if the machine is operating at low load, say providing grid support, okay, then you might see an uptick in the internal void discharge behavior. And the winding temperature, if you're also doing winding temperature monitoring over time, if there's gross delamination because there's air pockets in the voids, the thermal conductivity of the material reduces. So you may also see an uptick in the machine winding temperature as a consequence of, large distribution of voids within the winding insulation system. Through your offline tests as well, performing capacitance and DF tests, you would see increases in DF and a reduction in capacitance potentially. And the failure the degradation rate for this type of defect is quite long. This is the natural aging of a generator, so you may expect to see progression over 25 to 30 years. Okay. Thermal cycling defects, this is similar to void defects mentioned on the previous slide, but where the voids are directly adjacent to the copper conductor. Okay, this is something that can fail with much shorter progression to failure. I put 10 years here, but there are some shorter estimates as low as 2 or 4 years. And the characteristics are distinctive. Notice the asymmetry now where the discharges are higher on the positive half cycle versus the negative. And we would look for the polarity of these pulses is actually negative. And if the negative polarity pulses are significantly larger than the positive, this can be a warning or an indication of this type of defect. Again, we see a relationship to the operating conditions. So for this type of defect, the relationship with temperature is that you would see a reduction of the PD up at higher temperatures. Okay, so it's inversely proportional. For loose bars and slots, okay, so this is where you have vibration of the bar within the slot. Mechanical and thermal stresses fatigue these components within the winding, and eventually over time, due to the magnetic forces, you can have vibration of the bars and the slots, which abrades the surface of the semiconductive. So this semiconductive coating on the bar coil surface is intended to provide a solid ground, bonding between the bar or coil itself and the stator core. When abrasion wears this down, we end up with partial discharges at these sites. Okay, and those partial discharges can be directly correlated with operating conditions here if we look at discharges occurring at higher loading. Okay, so at higher loading, the magnetic forces cause vibration, which can lead to vibration sparking, and that abrasion creates damage to the semicon, which can ultimately lead to failure. Okay, failure in this scenario can be quite short, and of course, if the bars are loose, if there's any major system disturbances, you can have a failure because the bar not being rigidly held, the magnetic forces imposed on the winding during a fault event may cause a massive disruption to the winding due to movement and ultimately a failure. Similar to the previous one, end winding vibration again is correlated to operating conditions. So if you're performing continuous online PD, we would look for the PD behavior up at higher loading. Okay, and vibration can lead to a whole slew of issues with the core and the clamping structure. If you lose, things like clamping fingers, it can cause additional abrasion at the regions near the end winding. Okay, and this would be very similar to the loose winding pattern behavior, but again, we can have short times to failure in these instances as well. So this table gives a kind of overview of how we would assess different discharge types based on kind of these characteristics in terms of their relationship to operating conditions. We can see many of the major defects have a relationship to either temperature or loading. Okay, in the cases of some end winding issues relating to contamination or discharges in end winding, there's relationships to other operating conditions such as humidity. Okay, so our online sensor that we've constructed for online monitoring of PD called Intego is focused around performing measurements in this way. So collecting the online discharge data over a range of different operating conditions. So we see here, this is actually a schematic from IEC 60034-27. And in that guide, they actually prescribed to do the periodic partial discharge test at a range of different operating points. So going from low load to high on machine startup, waiting for the machine to thermally stabilize, then reducing load. And at each of these points in transition, okay, they're asking to perform PD measurements at these points. The rationale for that is, of course, based on the table and the failure modes we talked about previously, that different defect types will reveal themselves for different operating conditions. So our online monitoring data is monitoring continuously the information at different load and temperature points passively. It would be very impractical to require this sort of measurement at different operating points, load and waiting for temperature stabilization in an installation in the field because O&M costs would be very large. It takes quite a while for machines to thermally stabilize in some instances, and to go through that regiment of going from low load to high load, waiting for temperature to stabilize, that will require some augmentation of other units at the plant. So juggling load between units to ensure that you go through these transition points and taking these measurements can be very impractical in a periodic measurement, okay? But if it can be done in an online sensor that does this automatically through normal machine cycling, you would collect the same information from continuous online monitoring, okay? So saying we collect all these data points and we have the severity of the partial discharges indicated here for all these data points, we're now able to extract information about where the partial discharges are most damaging. So colored in red, we can see in this case high electric discharges in this region of the map. Okay, so at low loading, we see higher partial discharges in this example. Here's an example here of discharges from a 300 MVA 19 kV unit. And you look at the assessment here, we see in the lower loading regions, we have only kind of void discharges, and these are lower discharge intensities. Notice the color green. But up at the higher load regions and higher temperatures, particularly above this threshold in temperature, we can see another pattern in the PRPD reveals itself. And this pattern is indicative of slot discharges. Okay, so the customer, once they performed a boroscopic investigation, looking at the slot section, they've seen indications here of slot discharges in the winding. Okay, and this is one of the more serious failure modes that can be shorter progression to failure. And this finding, the ability to see and distinguish the difference between operating at the lower load and temperature and the higher loading PDs revealing themselves, this is quite beneficial. So if only doing a periodic test, of course, and you're obligated to do the measurement at lower temperatures or lower loading, or you just chose a period in time seasonally that the overall temperature was generally lower, you may not see this defect, right? So the ability to have this data collected passively through continuous online monitoring and trending and being able to interpret the data relative to temperature and loading information is very valuable. Here's another example of an air-cooled winding. Okay, so we see here this 32 megawatt hydro generator. We're collecting partial discharge data. We see the pattern here, but we can also see that the trend later in the season here, like towards the cooler winter months, we end up with higher trends in overall partial discharge. And it's related to, or inversely related to, the relative humidity in the air. Okay, so we know if you look at IEEE, there's actually guidance here where discharges in the end winding regions are expected to be higher during low humidity conditions. And as we approach winter months, of course, for this utility where it's located, in the winter months, as temperature cools, the relative humidity gets lower. And we can see through the correlations of air inlet temperature, relative humidity, we see the red region here indicated higher magnitude discharges, but also the discharge pattern also indicating to us end winding discharge. Okay, so a lot of information is available here through this correlation. We can see where the discharge magnitudes are the highest. We can see high fidelity partial discharge pattern, and all this is informing us to look at and possibly consider cleaning of the end winding regions based on the condition that we get through the online monitoring data. So some key takeaways. The modern continuous online monitoring for generators provides benefits over some of the older conventional approaches. Okay, and high fidelity phase resolve diagrams are useful for identification of stator defects. So we've seen that in the previous cases, that by having the continuous data, having signals that are well denoised, removing any external interference, we can see very clear partial discharge patterns with high sample rates and very clear patterns that we can compare to documented known defect types from industry standards. And the continuous monitoring, it facilitates trending of certain defect types. So in the previous case, we can trend seasonally. We can look at each winter, is the end winding discharges getting more serious, okay? That would be very hard if we didn't have this ability to do the trending relative to the operating conditions, because the operating conditions for humidity, ambient temperature is going to change over time. All of these things can affect the partial discharge patterns and their magnitude. We really want to be able to compare like for like. So if we want to compare the seasonal variations in the discharge magnitude under those lower humidity conditions each year, we have the ability with a tool like this, right? And of course, the ability, this just is related to the previous point, but many of these defects are correlated to load and temperature. Many have distinctive PRPD patterns, and by combining all of these elements, we have the best ability to interpret our online partial discharge data. Okay, and that would be everything. Thank you for attending.
Okay, thank you, Nathan. Very informative presentation. I had a look to the chat, and we have some questions for you. Let me start. The first one I selected is this one. What is your opinion about the partial discharges in hydrogen-cooled turbo generators? Do they exist? If so, can they be dangerous?
Yes. Okay. So generally, in hydro machines at elevated pressure, partial discharges would be lower than in the case for air-cooled machines. So I understand the consideration that maybe partial discharges aren't as relevant in hydrogen-cooled. I think it's a misnomer, because although many of the surface discharges and the external discharges would be unlikely to incept in those regions, you can still have very serious defects relating to the slot discharge, vibration, as well as internal void or delamination related discharges. So I think it's a misnomer, just because customers may see lower overall discharge activity because many of the surface or external discharges are kind of sequestered. But in reality, over the life of the machine, there will be defects that arise, and partial discharges would be present on those machines.
Okay, thank you. Next question is about the sensors. Coupling capacitors is not the only available sensor. What about stator slot couplers?
Okay. Yeah, so stator slot couplers are they are good in the sense that they provide a very well denoised signal just inherently. So these are sensors that are installed directly within the slot where the bar is located. Okay. The problem is that their monitoring is very local. Okay, so you just have essentially monitoring of the bar or coil where that sensor is installed. That's very different from the capacitive coupling sensor, which has some ability to see into the winding. Okay, so I think for coverage and detecting problems through a larger portion of the winding, there's a greater advantage with capacitive coupling sensors than there is for stator slot coupler sensors.
Okay. The last question is again on the sensor, and this one is specifically on coupling capacitors. What size of coupling capacitor would you recommend?
Okay, so there are kind of two traditional sizes or common sizes in terms of capacitance. So a lot of machines may be previously equipped with 80 picofarad coupling capacitors. Um, these are these are like quite conventional. Okay, so the subset of sensors at 80 picofarads would be probably larger than 1 nanofarad, which is the other common size. Okay, um, which one would I recommend? So the 1 nanofarad sensor is going to have better sensitivity for monitoring deeper into the winding. So for this reason, my inclination is to, if you're installing on new, that you would consider installation of a 1 nanofarad sensor because it would provide better monitoring at a greater depth into the winding. Okay, but for generators pre-equipped with 80 picofarad sensors, and they're terminated externally to the generator, this is fine, and that many monitoring systems can interface with those pre-existing sensors, so as not to create a major maintenance activity to have to install new sensors at 1 nanofarad. But that would generally be my comment or my guidance on that.
Very well, thank you.
Okay, folks. Nathan, first of all, thanks very much for the presentation today. Hopefully everybody found it informative. Obviously, to everybody on the call today, thanks very much for taking time out of your busy schedules to dial in. And also thanks for those that attended our first webinar a few days ago. Both of our webinars will be available on demand for all attendees. So if you can please just keep an eye out on your emails over the next coming days for your link to the recordings. Unfortunately, we haven't been able to get through everybody's questions today, but we do have a note of them all and we will reply back to everybody individually. Don't hesitate to reach out if you have any questions, any follow-up questions or feedback. You'll actually find my contact details. My name is Seamus McElmurray in the chat section. And thank you once again for your participation. We look forward to connecting with you again. Have a wonderful day. Thank you.
Thank you.
Thank you.